Welcome everyone to FP Forum, which a long time ago when we met in person was basically let's get together and talk about functional programming. It wasn't necessarily talks. People would bring things in and work on various problems or just chit chat or commiserate about object-oriented programming or whatever. It was a local Berlin community event. And we haven't been able to do that these past few months. So what I've been doing instead is having individual speakers come and do talks, kind of reaching into my network of functional programmers from around the world. But I really felt we were missing something because talks are great, but interaction is also good. And I don't know how to recreate interaction in a convenient way in Zoom. But I thought having people present maybe smaller topics or quicker topics, work in progress, might be interesting for people as well, especially for things that maybe don't warrant, for whatever reason, a 3-hour talk as we've had in the last few months. And this could give us an opportunity to exchange ideas a bit more, have a bit more conversation. Let's just see how it goes. So we have 3 truly excellent speakers lined up for tonight. I'm actually very excited that we were able to get such esteemed people. Flavio Corpa, Torsten Scholak, I hope I'm pronouncing that correctly, and Richard Feldman. And normally I do an introduction of the speakers, but I'm going to let them introduce themselves when it is their turn to speak, and then let them control the show. First of all, if everybody present could just type into the chat where you're from, let our speakers know where you are. We generally have a very international audience with a slight tilt toward Berlin, which is gratifying. Cool. Thank you very much. If anybody has an announcement, we can do, maybe we'll do announcements at the end. Just remind me, you can put your announcement into chat. And we never have announcements, but I always ask. So if someone has a job opening, or you're, like if you're hiring or you're looking for a job, or you know some other event that you want to publicize, please feel free to do that.
Okay.
Not right now. Not right now.
Sorry.
No worries. We'll do them at the end because usually people join in the middle, and therefore no one will miss your announcement. I'm going to put some links into the chat, so you can follow us on Twitter. You can check out our YouTube channel. As a reminder, this talk is being recorded, and you can join us on the gigantic, I don't know, it was very small when I joined it. Now it's gigantic, the FP Chat Slack community. We have a Berlin channel. And finally, if you would like to support the Berlin Functional Programming Group, we have this extremely attractive t-shirt that I designed because obviously that's one of my skills, design. I think it's cool. Go to Teespring and order one. You don't have to get it in yellow. I really like the yellow. It feels like a very Berlin color to me, but my wife doesn't like this color. You can get whatever color you want. And I appreciate it. It helps me pay the Zoom bill. So that's it. I'm going to hand it over to Flavio, and I think it would be best if you don't unmute. If you have a question, I would type it into chat, and then we'll do Q&A at the end of each talk. Otherwise, it gets to be too complicated. So Flavio, thank you for joining us, and take it away. It's all yours. Let me just spotlight you.
Perfect. Thank you. I'm going to share my screen, and let's see what happens. So can you see my screen?
Yep.
Okay. Well, so my name is Flavio Corpa. I'm Spanish. I know I don't look very Spanish. You can actually not see it because I'm kind of redheadish or blonde, but I cut my hair so I look brownish. But I'm very white of skin, so I don't look Spanish. So people always wonder if I'm Spanish or not. It's kind of a meme for me. And I work right now as a Haskell engineer at 47 Degrees. And a company that focuses mainly on functional languages. We do mostly Scala, Haskell, Kotlin, and Swift. And we are always playing around with other functional languages, and we enjoy experimenting and also evangelizing about functional programming a lot as well. So I'm trying to share in this talk how to build your first GraphQL server using the library we've built, which is called mu-haskell. This is a family of libraries that 47 Degrees sponsored. And the first interpretation or the first incarnation of this library is called mu-Scala, which is basically a framework in Scala to build microservices, focused mainly on protocol buffers and Avro files. And we ported, or we interpreted also this incarnation of the library in Haskell, and it's called mu-Haskell. But in mu-Haskell, we went a step further because as I'm an ex-front-end engineer, I loved GraphQL, and I convinced my friend Alejandro, which I think it's also joined the the stream, the Zoom. I convinced Alejandro to try and make code in such a way that it would be reusable as a GraphQL endpoint, if that made sense. And that's what we did. And the library, the Haskell library that goes along with mu-Haskell and helps you to build basically a GraphQL endpoint, it's called mu-GraphQL. And it's interesting, I can show you more resources later, but basically, if you have an existing gRPC microservice working, you can do very little code and export that as a GraphQL server for free if you use, obviously, mu-Haskell. So I think it's something nice that we did there. So I'm going to talk about how to build your first GraphQL server with mu-Haskell. Maybe you're not familiar with GraphQL, we'll say, but it's just a query language for APIs. And it's not the topic of this talk to explain what GraphQL it is, because that can be a whole topic on its own. So I hope you're familiar with it, and if not, maybe in the questions I can answer more questions about GraphQL on itself. So basically, you start with the schema, because we consider in mu-Haskell that the schema of the GraphQL or the schema of your protocol buffers or whatever is your source of truth, and we're going to try to use that schema to generate Haskell code or type level representations of your schemas to make you type as less Haskell code as possible. So we start very easily. We are going to have one type, which is a book with a title and author, and then another type, which is author with the name and its books. And you can see that the types are recursive within themselves, but for GraphQL, this is totally fine. No problem at all. And then you always have to have another type called query, which are the possible queries that you can throw to your endpoint, and GraphQL will tell you with auto-completion what kind of things you can draw out of that query type. So in our case, we're going to start very simple. We're going to have an authors query that is going to return all the authors that you have, and similarly a books query that does the same but for books. So let's see how is it looking in the Haskell code. This is all the code that you need. I think it's roughly like 70 or 80 lines of code, but we're going to analyze it and go line by line to see what each line is doing. So let's start simple. We need a module main, as always, as in any Haskell application. Then we need a few imports. And the important ones, the ones that refer to our library, are these four last: mu-GraphQL, mu-Schema, and mu-Server. And if you have questions about this, feel free to ask me questions at the end. And hopefully also Alejandro will have my back if I don't know how to reply something, and we can have a more interesting discussion without taking too much time. So yes, what do we need after the imports? Well, you need 1,000 language extensions because, you know, it's Haskell. And also I didn't mention this before, but one of the approaches that we wanted to achieve with mu-Haskell was to encode as many things in Haskell at the type level as possible, because it was kind of an experiment to see how this approach would work out. We're very happy with the result. But obviously, if you see our source code, which is open source at GitHub, I can share the link later. It requires tons of the most crazy / magic / fancy types. and extensions. So I'm sorry for that. Maybe we will make it more approachable in the future. In fact, we wrote a paper about this and we presented it in the Haskell Symposium. What were our findings? What did we learn in the process of building this library? And it's an experience report of 11 pages, and maybe I should share the link afterwards as well. I think it's interesting from an academic point of view. Also, you can add additionally, this is line which is completely optional, and it's because I'm a warning freak and I cannot, if I see a warning in my editor, I just can't ignore it. So I toggle this flag in GHC to tell that I don't want to see this warning of partial type signatures, and we're about to see why it is needed. And this is where all the magic happens. So basically what we're going to do is we're going to have a very basic hard-coded library in mu-GraphQL. And of course you can modify this example and integrate it with something like a persistent or with a real database, and then implement your solvers in a way that they are meaningful, but we're just going to hard code everything just so that you see the amount of code that you need to build your first GraphQL endpoint with mu-haskell. There are other libraries in Haskell to build GraphQL servers in Haskell, and their approach is different. So you might enjoy our way of doing things, you might not, but we can also discuss that. And also we're always open to hearing feedback on our GitHub issues as well. So what we do? This line, obviously we are leveraging the power of template Haskell. In fact, I did all the template Haskell involved in this line, which was quite painful. But we take all your GraphQL schema and we turn it into a type level representation in Haskell of that schema. And that is going to save us a lot of trouble. Then we have our main function, as in any other application in Haskell, and we're just going to say that we are going to work on the port 8080, and that we are going to run our GraphQL query, because in GraphQL there's the concept of queries, and there's subscriptions, and also there are mutations. So we have like different servers that you can start up to start your Haskell server. And if you're just going to have queries, we have this handler. And if you need queries and mutations, we have a different handler. That's why the name is so specific, but that's basically it. And then we have a new type that we have to define, which is the service mapping. And let me explain this very briefly, because this is some of the things that sounded very weird to me at the beginning. So basically your GraphQL schema is like a tree. And what you need to define in this type of service mapping, you can name it whatever you want, but it's the leaves of this tree. What is the actual data that you want to query, that you want to get back when you run this GraphQL query? We said that we're going to represent books as a tuple. I don't understand English. A tuple with two texts, and our author is just going to be a name. We don't have IDs, so we don't have anything related to that. We have a slightly more complex example in our repo, in the examples of our GitHub repo. An example with IDs and with persistent, integrating it with an actual database. So this example is just as easy as possible, but we have many other more examples in our repo that you can check up later. So this is basically the type that we need. This is the hard-coded library that we're going to pre-fill with some data. We just have three authors, Robert Louis Stevenson, Kant, and Michael Ende, and one or two books per author. And this is the actual server implementation of your GraphQL server. So things that might seem strange at the beginning is this monad server. This is our special monad server that we have in mu-haskell. It really is not something special. It's just a server that allows you to do things in I/O, and as well, it allows you to throw server exceptions in case things go wrong. But we try to be as polymorphic as possible. And also, if you remember the warning that we turned off on GHC about partial type signatures, this is where we need it, at this type at the end, because this type represents the whole GraphQL schema, and it's just enormous. But it can be 100% inferred by the compiler. In fact, if I have time later, I can show you in the editor. It's quite amazing. And it writes you the type, but we don't want to see it because it's just not practical. So we put a partial type signature. And then you might be wondering, okay, in our server representation, we have objects, we have fields, and we have methods. And then we're saying with type applications, okay, this is my title, this is my author, and I have weird functions here like book title, book author, author name. What are these? Well, these are just the resolvers, because obviously this is the only part that you should care about when you are building your GraphQL server. It's how are you going to resolve each individual leaf of your schema, of your tree, so that when our server puts everything together, it's going to be to return whatever that you're expecting. So in this case, you saw the representation of our data. So the implementation is not actually that important, but this is something that is the only bit of work that you really need to do to get the Haskell GraphQL server working. So for example, for the book type, we said that we were going to represent it as a tuple of two texts. And this is how we would resolve the title and then the name of the author. It's just a pattern match. And then if we were going to resolve the author, there's a bit of more work involved. As you see, author name is completely trivial, but the author book is not so trivial because we're dealing with maybes there and a find if we need to deal with maybes. And also with the partial tuple syntax. And the important bits, I would say, are the actual queries. So if I call the all authors or all books handler, what is going to happen afterwards? And we have a list expression here and more Haskell, but it's basically, it's because our data is so ad hoc, the implementation is like that. So as I said before, you can implement this however you like, but this is basically what you have to do. That is all. So do I have a couple of, or just 1 minute, maybe, Steve, to show this working? Is that possible?
Yeah, absolutely, please.
Okay, perfect. So I'm going to share this. So let's see, I put a README here because I forget things. And okay, stack run. No, I'm not in the correct folder. So stack run library. And you see that our dev server, this is the code, is exactly the same as the one I showcased. This is the magic that you can see here. I don't like the partial type signature. Do you want me to autocomplete the type? No, thanks, but thanks for asking. And then let's open here a GraphQL playground. And okay, I need to say that it's the HTTPS. Okay, and then I am running my first GraphQL server, and I'm going to run the first query. So what's nice about GraphQL is this, that you, for example, you know ahead of time what are the things you can query and what are the things you cannot. So I'm going to query authors, and I need something. Okay, I want all the authors' names, and then I just have the names. But I want also the books, and I want to know the title of these books, and I can know that. And remember the recursive stuff. You can also know from this book the author and the name, and you can you can do a kind of crazy query, but it will be that's the magic of GraphQL. That basically you can do all these kinds of stuff and also tailor your data of your queries to the very detail. And this is meant to be like an inversion of control to the front end, so that the front end knows exactly what he needs, and you build the appropriate query for that. So let's see. going back to the presentation. Well, check it out. It's Higher Kindness. It's one of the open source repos organizations by 47 Degrees, and the repo is called the mu-haskell. I am Flavio Corpa on Twitter. You might want to ask me something or we'll catch up later. And that's what basically that's it. Thank you for listening.
Cool. So if anyone has questions, maybe type them into chat and then we can go through them one at a time. So I have a question. It's actually kind of an opportunity for you to do a marketing pitch.
Nice.
Because I use GraphQL.
Oh, perfect.
I'm curious, like, how would you pitch it to a development team that is very likely accustomed to developing mostly in JavaScript? What is the advantage of using your server instead of just like Apollo, say?
Well, this is very interesting because what we have done for the backend for GraphQL in Haskell would be similar to what Apollo does, but for Node. And I would say that the main advantage is that you can do your GraphQL server in Haskell, obviously, but then we get into a different question, which is how do you market Haskell for a backend team that it's used to do Node stuff? So I think it's a different question.
Yeah, okay. Maybe a full stack team that is used to just working strictly in JavaScript, but that's like a bigger question, sure. The only other question for me that came up, other than why you're using tuple sections, was, well, my feeling when I was developing GraphQL is that the most tedious part is having to write resolvers. And yes. I know there are some tools to generate those automatically from a schema to some extent anyway. I don't suppose you have any kind of solution like that.
Yes, we are aware of other solutions, but there's a trade-off always. So if you get the resolvers for free, then you need to have like types for all the internal representation of the schema and the types. And this is, for example, what other GraphQL backend libraries for Haskell do. But we decided with this type mapping magic type to do it the other way around, so that the server doesn't really care about what's in between, and you just care about the data that you're getting back from your queries. And it's a different approach, but it works out, and it's something that everyone needs to value regarding, I think this is really complex, or I like this, but I don't like the magic that is going on behind. So I'll maybe use something that is a bit less magic. I don't know. I don't know if that answers your question, but.
No, yeah, I mean, actually looking at the code, whereas people often complain about the terseness of Haskell syntax, I mean, this could be an ideal use case because you end up having to write a lot of convoluted resolvers in JavaScript, but with Haskell, you can make it very simple. I mean, especially with what you demonstrated using like list comprehensions or whatever.
It's true.
Looks like some people are making comments. I don't know if there are questions exactly. Pablo, did you have a question, or do you want to unmute and ask something?
Yeah, I was really enjoying what you're saying, but there's a moment where I feel like I missed a detail. This is something you're using in production, or?
Not yet. We just built the library, and our colleagues have mu-Scala code in production. But since mu-haskell is the latest thing that we built, we're looking for people to use it and listening to feedback. And we know that some people is using it, mostly the protocol buffers servers in mu-haskell, and also people is trying to play with it in GraphQL. But for now, we don't know for sure if anyone is using it in GraphQL. We don't have a specific client for Haskell that needs a GraphQL server, so that's why we couldn't use it in production yet. But yeah, that's the answer to the question.
But you do think, it sounds like you at least think it's plausible that you could do so.
We think it's perfectly plausible because, as said, we have more complex examples that use persistent and other wrappers for databases, and we have more examples with, that are not trivial like the one I showed, and they work perfectly, and you have a working GraphQL server. So if it works, then I don't see why it wouldn't be a fit for a production application code. But obviously, we're also very open ears about the issues or the things that are making people maybe difficult to implement this, and we try to be as responsive and as helpful as we can in GitHub. So if you are the first one that is going to try this in production, we will be very, very happy to help you.
I'll probably be playing with it just to play with it. I don't have any production stuff either for it right now. But yeah, I think usually the question of that is just like, well, no, we're gonna change the interface a lot would be the time when you say it's not. But it sounds like it's good. It looks really cool. So thanks.
Nice, thank you. Any more questions, maybe?
I don't think any other questions. There's a comment from Vincent who doesn't have his mic set up, and
Vincent or?
yeah, looks like
Okay.
those value functions would work well with lenses. I don't know if you want to talk about lenses.
Yes.
Seems astute.
Yes. If you check the examples in our repo for more complex things, we have like, I think the complex server we have is using protocol buffers, but it is a more convoluted server example of we build like 3 different microservices with mu-haskell, and we have like a pool of choices in which you can try and build the resolvers or the implementation of your microservices like in flavors. You can use, for example, product types, you can use type applications, and the latest thing that we implemented was mu-optics. So they are lenses to help you build these microservices with lenses. So for this basic GraphQL example, I didn't think it was appropriate to mix it with, okay, we have another library called mu-optics, so you can also use lenses in this GraphQL server. So we tried to make it constrained, but yes, for sure, for your getters and setters, we are totally aware of the use of lenses, and we're using them, in fact, in one of the flavors for building microservices.
Maybe in the future you can do a longer talk as a follow-up. Maybe you and Alejandro together can team up and do a more in-depth presentation at some point. This was very cool. I have to admit that while I was using GraphQL, I found myself enjoying it quite a lot and also feeling guilty about it because of my Haskell background. And I wondered if I was allowed to enjoy it. And now you've brought them both together for me and given me a nice excuse not to feel ashamed anymore. So I hope I can find the time to play around with your library as well.
Perfect. One last thing that I forgot to answer is that, let me share my screen again very quickly, is that this talk, I uploaded the slides and the code examples to GitHub. So maybe you can, Steve, share the link in Twitter or anything afterwards, but basically you have the code for the slides, how I built my presentation, and the Haskell example itself, in case anyone wants to have a deeper dive, and if not, all the information is in the GitHub repo that I mentioned as well.
Yeah, if you put the link into chat, and yeah, I'll tweet it out later.
Perfect.
For sure. Okay, then let's move along to Torsten. I think Torsten was an audience member in one more thing about Flavio. Flavio has been extremely patient. I think you volunteered to do a talk like 3 or 4 months ago, and you've been waiting until we had more people. So thank you for your patience.
Thank you for having me. For sure.
Torsten was an audience member at one of the prior meetups, and I think maybe it was Stephen Deal's talk, and yeah, he gave you a shout out, and then I checked out your GitHub and I'm like, I have to get this guy to do a talk. And I'm really grateful that you were willing. So Torsten, please, the floor is yours.
Thank you very much, Stephen. Well, thanks for the opportunity. I mean, I didn't expect it, and it's definitely a great pleasure to give this talk to you today. I'm actually calling from Eastern Quebec, so I'm on vacation. That's a cottage behind me, and my wife is here next to me, but she's not participating, just listening. Also, thank you, Flavio. This was a great talk, actually, and maybe I'll have a look at this as well. Although this is not my turf, GraphQL is quite interesting. Yeah. So today I will talk about a framework, or which is, I should say, a library that I've been building together with a great team. Actually, I joined late to this enterprise. So like when I joined, there was already 2 years of development prior to my arrival. The library is called Hasktorch, which is like an amalgamation of Haskell and Torch, who well, if you don't know, Torch is a big machine learning framework. So today I will talk about Haskell and machine learning, and that's a bit of a novelty. So first, let me share my screen. You should see my desktop now, and the slide deck will be coming up now. So can you see this? I hope so.
Yes, yes, we can see it.
Cool.
Yes.
Right, so the library is called Hasktorch, and it's a library for tensor math, and we call it differential functional programming. So the word differential is just like taking derivatives. So it's about taking derivatives of programs and doing stuff with those. This will become more clear shortly. So first, a shout out to all the great collaborators that I'm interacting with and that I have the pleasure to work with. So there's a team of core contributors that I call myself a member of. So there is Junji, Austin, Adam, Paske, who is one of the core members, or was one of the core members of the PyTorch framework. And I think was one of the founders even, or initiators of this project in the very beginning. There's me, and then there's Sam Stites, who is also together with Austin, I think, and Adam, the original initiators of Hasktorch, the library. And then later Junji joined, and I think I was the latest addition to the core contributor team. Apart from those, there was some collaboration due to Google Summer of Code. So this is now the second year that we've been doing this. And in 2019, we had 2 great students, and I actually never interacted with them, but they worked on, I think, NLP-related questions, and also how to combine tensors and functors. And this year we had a great student, Andre, who has been working on data loaders for Hasktorch, and has made some great contributions with regards to that. And apart from that, we also have many community contributors. Just a shout out to a few of them. Chiara, she has just finished her thesis, and she has been using Hasktorch to basically build and do her thesis on program synthesis, and many others that that deserve to be mentioned here. Okay, so yeah, there we go. What is Hasktorch? So maybe you've heard of PyTorch. PyTorch is actually one of the industry-leading machine learning frameworks. So if you want to do like deep neural networks, machine learning anywhere, any company, you either use PyTorch or you use TensorFlow, and there's actually nothing much else. So TensorFlow actually started earlier, and then PyTorch basically took over the world almost, because it's a bit easier, and like TensorFlow had the issue that you couldn't, like basically you had to, well, you were in some sort of like execution context, and everything was a bit clunky and error messages were bad, and then PyTorch basically made this much easier to get around this problem, and you didn't have to like basically run your execution environment to get answers, but directly basically interact with the system. And it's like much, I mean, favored by researchers, because you can express your ideas very well. Whereas TensorFlow is more like the framework you would choose if you want to have like a stable production environment. I think this is still where it leads, but PyTorch is also making headway there. Why is that? Because PyTorch is actually built on top of a very stable core. It's called libtorch, and this is a production grade C++ library of tensor math. So PyTorch is basically the Python framework built around this foreign C++ code that powers it underneath. And because of the separation, we had the opportunity to build another front end basically to that libtorch library, and we called it Hasktorch. So Hasktorch is also built on the same foundation as PyTorch. And in theory, you could reach complete feature parity with PyTorch, although there's a small team that is maybe out of reach, but we can come maybe quite close. So because of this fact that Hasktorch is also built on top of libtorch, we can get GPU accelerated automatic differentiation basically for free, because this is all handled by libtorch already. We don't have to implement automatic differentiation of tensor programs in Haskell. Although this is interesting as a challenge and interesting for many like reasons you might have, like math reasons, or like just because you want to play with this, or because you think like maybe there's like a simpler truth to automatic differentiation than it is established in the bigger frameworks. For us, this is not a concern because it's already taken care of. The novelty of Hasktorch is, though, first of all, it's in Haskell, and the second is we have not only an untyped Tensor API, which is kind of like in the spirit of PyTorch, we also have a typed Tensor Math API, so we can track properties of tensors in the type system and make it more like correct and more stable to use. And the Hasktorch library comes with many examples. So we have programmed examples for image classification, regression, language modeling, and also distillation, among others. So one of the pain points of PyTorch, though, is that, and you can look this up on the internet, when it comes to using tensors and write programs with them, you always run into problems with shapes mismatches. So you write tensor ops, and then at runtime you find out, oh shit, these two things that I wanted to compose there, they actually don't compose, because one outputs a tensor of that shape, the other one wants a tensor of another shape, and at runtime you get a tensor shape mismatch error. And if you Google for that, PyTorch shape error, I mean, I did this 2 weeks ago, so there were like 324,000 results for that. So like people run into this a lot. And in Hasktorch, I mean, even though it's possible to still generate errors, they are typically caught by GHC in advance. So like you don't have to run your program and maybe after like pushing it to some sort of training environment has to have, I mean, you will not get failed jobs. What you get instead is a very tight iteration loop because of GHC that checks your tensor shapes, your tensor data types, and also the computation devices. So whether you run this on CPU or on GPU, even before you run the program. So I have prepared a little demo. So what I will do now is I will turn off the slide deck. And nope, I will turn off the slide deck, right? And I will switch to VS Code, if I can find it. Hello, where is it? Sorry, there it is. So here's a little program. There are lots of imports. It's not as clean as the mu-haskell or mu-GraphQL environment. Not polished at all. I tried to keep it simple. So like Hasktorch is still a very young project and many things are in flux. So we haven't really made like much effort to like make it really nice for the user. But bear with me. So like basically what I will show you today is a regression example. So we're trying to approximate a function, but we're only allowed to look at data points of that function. So we're not, like, we don't a priori know what the function is, but what we do know is that some input-output pairs of that function plus noise. And the function I've picked for us today to look at, to basically infer or to learn, is the sync function or the sine cardinal function. So like, if you go to Wolfram Mass, you can see how this function looks like. So this sync function, x-axis, y-axis, and you can see it's like this squiggly line that has a peak at 0 and otherwise like tapers off with an oscillation. And it's defined as sine x over x. So this is the function we're gonna try to learn, approximate. And we're not taking the function as is, we're actually adding a bit of noise. So here's a version of sync that with an epsilon adds some normal noise on top of it. So it's like relates to sync A plus epsilon times noise. And then there's some other things here. So for instance, there's a data type that will hold the data set of input-output pairs for that noisy version of the sine cardinal function. And then there's a smart constructor for that data type, where well, basically, like I say, what the name of the data set is, how many data points I want, and then I will just create that data set and push it into memory. And since Andre has worked on data loaders, we also have this construct here. So there's a dataset type class, which is defined here. So basically, we equip him this data type with two methods, a get item method and a keys method. So it's basically you want to pull out of this data set, and you want to maybe see how many or like what sort of items are in there. And this is made through this data set type class. And what it also gives you for free is a buffer and concurrent operations with this data set. So you can like basically move much of the computation of the data set into worker threads that basically prepare that data set in the background and make execution fast. Because what you never want to do is like have a very slow data loading loop that will basically starve your GPU for computation because it has to wait for the data to arrive. And then later in this file, I mean, it's like 300 or 400 lines. It's not quite as short as the other example we saw today. There's a training function. So basically this will be used to train our model that we will build in a short time. There's an evaluation function to basically probe how good our learning has been. There's an inference function to actually use the model downstream. And then there's some types that define parameters. I will talk about this later. And then we have our main program. So in the beginning, we will create a model, then we choose some things, and then we have a main loop basically that goes over the data set many, many times. And each time the data is inspected by the model and we train on the model on the data. This is called an epoch. So one epoch is basically one full loop over the data set. So basically the loop that we have here, so there's like a fold here. Each step of that fold is one epoch. Okay, so we have a bit of idiom, or like we have worked out some idioms for Hasktorch. So actually the first thing you have to do is like you have to define the data type for your model. And I can start with an empty model. So just call this model, and it has one constructor called model. And let's define a show instance for this thing. And so nothing much has happened, but I had a hole here for the model. So what we'll do is now I will make a model here, save this, and then show what the Haskell language server tells me about errors that are still in this file. So I'm using GAC IDE or the Haskell language server here to get all the typing information that GAC provides into this IDE. So I get instant feedback about what's happening. So at the moment it tells me there are some problems here. So it tells me there's no instance has forward model, tensor, and so on. So basically that means that like our program doesn't know how to use the model yet. So in PyTorch, if you're familiar with that, you always have to define like a model class. So it's a module, they call this there. And you will have to have a method in this class called forward. And here we will have also a forward function, but the idiomatic way in Hasktorch to do that is you have to define has forward instance. Forward instance for this model. And you have to say what the input type is and what the output type is. So forward is basically one forward pass through the model. So we want to have a tensor. We want to have this tensor sitting on a device and to have a certain data type for that. And I made already type synonyms. So device is actually CPU and D type is float. And then we need a shape for this tensor. And I'm choosing here batch size, comma 1. So this is a type level list here. And it says the input tensor in this first dimension has size batch size, and its second dimension has size 1. So this is the input tensor, and the output tensor will be the same for this example. Why? Because we want to approximate this sine cardinal function, and this is a function from 1D space to 1D space. And that's why we have a 1 here. And we have this batch size dimension because we cannot, or we shouldn't look at the data all at once. We want to look at chunks of the data and use this in stochastic gradient descent. And the batch size type parameter here defines how large one batch is. So these are all natural numbers actually. So these are of type nat or kind nat. And then we need some methods. So the method that we have to implement is forward. And the first parameter is model. And the second parameter is the input tensor, t. And just put in undefined here. We need the second one, forward stochastic, which I will actually not use, but we have to implement nonetheless. And I will just use a definition which points back to forward. Right, so now what does it say? So it says no instance for parameterized model. Okay, well, luckily we have made this easily available through generic deriving. So we can add this here, but now it says no instance generic model. So let's add a generic instance as well. Okay, so we resolved all type issues now. Of course, this program won't run because we have this undefined here. So this will actually give me a runtime error. But before we go there, let's just use GHC, well, the interpreter, basically the REPL, to see what is going on in this program. So one thing we can do is actually, we can probe the number of parameters of this model. So remember, this was an empty model. So this data type actually holds nothing at the moment. And actually our GHC should be able to tell us that. So if I ask what is the kind, or what is the value of this type family called parameters on model, then it tells me there are no parameters in the model. And this is what you would expect because, as I said, this model is empty, it has no parameters. So there's also nothing to train at the moment. So if you have no parameters and there's nothing to train, then the only output actually this model can have is the input tensor. So the only logical way to implement this function at the moment, the forward function, is the identity. So we take a t as input and we use t as output. So there's nothing going on other than that. And so if we do that, so we can ask ourselves, well, our model is now the identity function. Will this actually fit our sine cardinal function? Well, probably not, because first of all, there's nothing to learn. Second of all, the model can never learn anything, and it will always produce the identity function as output. But we can actually look at what the model does, because lower in that file, I've made some additions which allow us to look at the inputs and outputs. And so let's stare at this plot here a little bit. Hope it updates quickly. Now it's still compiling. Just a second. Hello. Yeah, there we go. So it tells me actually now, after it compiles it, the average training loss is 4.1 and the average evaluation loss is 4.2. Okay. And it stays that way, which should be the case because so every output here is after one epoch. So if there was any change because our model learned something, we should see any change, some change in these numbers, but the numbers stay the same because, as I said before many times, the model doesn't learn anything because it has no parameters. So how does it look like? Well, here the very thin black line is actually the ground truth. We're not supposed to look at this actually because in the general case we don't know what the ground truth is, but here we know because we have defined this like pathological problem such that we know it. So this is the sine cardinal function, a sinc function. And then these dots around this is basically the data points of the evaluation data set. So this is randomly sampled data basically from the sine cardinal function plus some noise. So this is actually what the model is evaluated on. And then here, this blue line, this is the model's prediction at the moment. So it's the identity function and therefore it's just a straight line. And there's nothing more to it. So this will never improve, but still I wanted to show you that so that we have a baseline, a very bad one to start from. And here you can see in this other plot here on the x-axis the number of epochs. So we go up to 100 epochs here, so 100 times over this data set. And then here's the loss function. So it was about 4.2 in that thing down here, yes. So it shows me 4.2. I can refresh this and nothing has changed because it's not learning anything because there's nothing to learn. So how can we change this now? How can we make this model learn anything? Well, first of all, what if we cheat? What if we actually told the model what the solution is? Well, we could do that because now we actually know the answer. So if I implement the sine function, the sinc function in Hasktorch ops, well, I mean, we can do that and see what this gives. So this is basically the sync function, right? Sine of t divided by t. And this gives me also a tensor of this shape. So if I recompile this, well, this still has no parameters. Shouldn't have, because I only changed the forward function, but I didn't touch the data type here. So if I now recompile this and evaluate my model, we should get a near perfect score, because we're trying now to approximate the function with itself. So let's see what we get. So this will define basically the best possible result ever. So you see here. So okay, so this gives us 2.56 to the power of -5, and it's also not changing because the model is not learning anything. How does this look like in our plots? Well, as you would expect, the blue line is basically sitting on top of the black line. But of course, we're cheating here because we're imposing the answer. So let's interrupt this. This was just basically a sanity check. And let's add now some parameters to this model to make this more interesting. The way I'm doing this is like I'm using here record syntax, and I'm calling my first layer, then I'm adding here the first layer. And I'm choosing a linear layer. And this linear layer has some input dimensions and some output dimensions, and it has a data type, and it has a device. So here are two parameters, num in, num out, so number of input dimensions, number of output dimensions, and they have to come from somewhere, so I have to add them to the left-hand side of my model ADT. Right, so now I have to change this in several places because my original ones didn't have anything. So, okay, so like the number of input dimensions and the number of output dimensions, they should match these ones here, because the number of input dimension has to be 1 because this is one-dimensional function, and the output dimension is also 1. So actually this has to be a has-forward instance for model 1.1. And here we have to change the record syntax. And some other problems. Yes, it's complaining because we still have this thing here. So this is not a pure model anymore. This is now something that has state. And here what I will do now is I will sample the initial state of the model, so basically the untrained model, randomly. And the way to do it is you call sample, and you need a specification of how to sample. And so I'm having this constructor here linear spec, because I have a linear model and need to use the linear spec for sampling. But it's not happy yet because I have to apply these two types, 1, 1. So now it's happy, no problems anymore. Let's recompile this and ask how many parameters there are. Oh, it's complaining because I have forgotten here the numbers. Okay, so now we see this is a model that has two parameters, parameter 1, parameter 2. It sits on the CPU. It will work with float data, and the first parameter is a matrix of size 1 by 1, and the second parameter is a vector of size 1. So this model is actually two parameters that both are basically effectively just one number. This is a one-dimensional linear function, basically. Okay, so if we now recompile this and try to train, then we should see something different than we saw before. This will probably take a short time. There we go. Okay. Ah, I forgot something. I never changed the implementation of the forward function, so it's still the ground truth. But this can be easily fixed. So instead of like doing sin c here, sync function, we're just delegating now to the forward function of the linear layer. So we can call forward on first layer t. So just to see that the types line up, so we have here the tensor t. Then first layer is just this linear layer. And then this forward function here, has the same signature as our forward function. So it goes from batch size 1 to batch size 1. It takes a linear layer as input. So that all checks out. Let's recompile on the left-hand side and then also run on the right-hand side. And now actually we should get something different. So now the model will actually learn something, or will try to learn something based on the data we give it. And, no. It's not ready yet. Still the old plot. There we go. Okay, so now we have new numbers. Right. Okay. So it's basically first very linear. Okay. So it's basically flat linear now. Well, this is more or less what you would expect, like the best possible linear approximation to this non-linear function. And now here's something interesting. So it starts off as a high value, then it goes down to 10 to the minus 4, and then 2 steps later it goes up to 10 to the power of 23, and then it's not a number. So what we have observed here is actually gradient explosion. So what this means is, you can see it on the plot, so this explodes. This is logarithmic on the y-axis. That's why this is just this little jump here. So this model is now done. It's broken. We should not consider this anymore. And it also tells us that linear model is probably not the right choice here. Let's interrupt this. The answer is to add more layers, as you do in deep learning. So the second layer will be another linear layer. And now we have a choice to make about its dimensions. Let me just start by this. So now we have input, output, output, output. So if I asked the compiler now, oh, sorry, I have to change something. So now we have 2 layers, so we have to sample twice. Right. If I ask the compiler now, what are the parameters of this thing? Well, now we have 4 parameters, but they're still basically not really good. So there's one number, another number, so 4 numbers basically. So this won't work either. What we need is more dimensions. The way to do that is we need to spread out. So we need to add a hidden dimension that is larger than 1. So now what will happen is basically you go in with 1 dimension, then you widen up to number of hidden dimensions, and then you narrow down again. And we have to add this additional type parameter here and there. Then it complains that the forward function is not correctly implemented, and that's true too. So now we have 2 layers. So we have to use both. And oh, okay, so what did I do wrong here? It says something with broadcasting didn't work out. So this is the way of the compiler to tell us that I did something wrong. This doesn't look very nice, but the short story is of this very long story is that I have to swap them. So it's first the first layer and then the second layer. Okay, this looks better. And we still have one problem. No nut, none hidden. Okay, so I think I know what's wrong. Yes, I forgot it here. So here I have defined the type num hidden. Let's just use this one. So now we have 100 hidden dimensions. And sorry. So we see this now. So we have like 100-dimensional matrix, 100-dimensional vector, another 100-dimensional matrix, and then 1-dimensional bias term. So there are many more parameters now to train than we had before, and maybe it works now. So let's see again. Surely a model with more parameters has more chance of succeeding here. Okay, looks already worse. Oh. Yeah, so this exploded even more quickly. So what is the problem? The problem is that we didn't do anything interesting with the second layer. We just piped the output of the first layer into the second layer, and both are linear. And it turns out if you can compose 2 linear layers, you get another linear layer. So what we have to do is we have to introduce a nonlinearity so that this linearity aspect goes away. And to shorten time a bit, I can tell you that the right answer here for this little problem is to use an activation function, as they call it, called tanH. So this function basically looks like this. And what that does is adds an aspect of nonlinearity to this model. And when I use it, the output will hopefully look much better. It always takes some time here. Okay. All right. Yeah, it starts off a bit in a weird place, but you can see, first of all, it's not linear anymore. This is not a linear line. It's something Okay. 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 So maybe I see. It seems like it's getting closer to the answer, but it should certainly will take more time. So while this is going on in the background, let me tell you a bit about how this program actually works. So here's the training method. So the training method takes the model, an optimizer, the learning rate, which is a hyperparameter that you can tune, a stream of the input and output pairs, and returns a pair of a new model and a new updated optimizer. And the way it's implemented is as a fold. So basically we enumerate the examples that come out of our stream, and then we basically iterate over them. And in each step, we take the old model, we call our forward function here on the model with the x values, we get predictions for the y values, and then we use the two values, the ground truth that we have in our data set, and the predictions, and evaluate a function that tells us how good our approximation is. And in this case, this is the mean squared error. So basically, if the y prime is exactly y, this should be 0. And if it's not the same, then this will basically scale as the squared distance between the two values. And we call this the loss function. And this function is actually the average loss function. So what it will return is a tensor of 0 dimensions. So it's basically just a number. And then we call this helper functions here run step. Run step is basically just calling the backend, so libtorch in this case, to calculate the gradients of the loss function with respect to the parameters of the model. So like these parameters you see down there, these 4. Then is using the optimizer to come up with a new model hypothesis, basically, and a new updated optimizer. Sometimes the optimizer has internal state. And in that case, you get a new optimizer back as well. Not only a new model, but also a new optimizer. And you do this over and over again in one epoch many, many times. And so now we can see actually that the model seems to be quite good. Okay. So there's still some problems here. And I talked a lot about the model, but I haven't really talked about the optimizer yet. So let's look at what the optimizer is right now. So the optimizer here is defined as this smart constructor make GD. GD stands for gradient descent. Actually, it's stochastic gradient descent. In this case, the new parameters will be the old parameters minus the learning rate times the gradients. So this is the simplest optimizer you can think of in the setting to find an optimum. And there are better ones. So one of the ones that is used most frequently is called Adam. I've linked to the paper here. So this optimizer has actually internal parameters, so-called momenta, and has some hyperparameters as well that I've chosen here, like probably everybody else chooses. And to initialize these parameters, I have to give the Adam the parameters of the model, but basically only to get the tensor shapes correctly. And otherwise, the Adam optimizer will be initialized with zeros. So when I choose this one, first of all, let's make sure that still everything compiles. It does. Let me interrupt this here. And I will restart now. Then we should actually see progress much, much quicker and also better progress than before. So I can talk about much more than I've shown here, and there's some more things about evaluation and stuff going on here, but everything is basically a fold. Like in deep learning with Hasktorch, everything turns out to be a fold. So the main program is a fold, training is a fold, evaluation is the fold, inference is a fold. So everything is a fold. Oh yeah, I can see like it's better almost immediately. Or maybe it doesn't look like it, but I can see that the loss goes down much more rapidly with this other optimizer here. Okay, so maybe at this point it's good to make a stop and quickly go back to the slide deck, maybe without making it full screen. So the summary is basically Hasktorch brings GPU accelerated neural machine learning to Haskell, and you're invited to try for yourself. All that I've shown you today is on GitHub. There's a repository in my personal account. It's called 2-layer network, and it's linked here. And this is where you can find a solution of this little thing, and you can play around with. I added 2 layers, but you could try 3 or 5 and see how this goes. You can also change the execution to GPU. Here I said CPU because I'm doing this on a Mac, and the Mac doesn't have an NVIDIA graphics card, so this won't work. But you can also run it on CUDA. So like if you have an NVIDIA graphics card that has meets the minimum required CUDA capabilities, you can try this, and it should just compile and just work as nicely this on CPU, probably faster. And if you're interested in the project itself, so it's still changing rapidly. We're not on Hackage, so you may find an old version of Hasktorch on Hackage. Please don't use that one. We should actually somehow remove it, because the new Hasktorch it's much improved and has seen like more than a year of improvements over what's on Hackage. So you should use what's currently in the repo, and the instructions of how to get started, and contributors are welcome. And thank you very much. I guess that's it from my side, at least. Let's see what the plot does. Wow. Okay. So this is getting where I want it to be. Thank you.
Thank you, Torsten. So I think we have a few questions. There's a lot of enthusiasm. Everybody says that you and your team are super nice, as another incentive to get involved. And I think Flavio had a question or two. I'm not sure if they were answered, but for the sake of the YouTube audience, maybe he wants to ask again, just in case.
Yes, I wanted to ask, how can we get involved with the Hasktorch project regarding, for example, our demos, with things that you would do with PyTorch translated into Haskell will help, or if there are many features of the core features of libtorch still missing, what kind of contributions that we can expect to land in the project?
Thank you for asking. That's a good question. The easiest way to get in touch with is to visit our GitHub, and you will find a link there to an email that was just created for the purpose of asking to get admitted to the Slack space. So we have a Slack space that Austin maintains, and I think I have admin access there. So if you send me an email, maybe I can get you in as well. So there's a little community of people who are working on this project or just want to get started with. That would be the easiest and quickest way to get started. You may feel adventurous and try to get started on your own. At the moment, I wouldn't recommend this, because yes, there are many paths to success, but finding the one that suits you the most is difficult, and you may find it more difficult than you anticipated. And I'd rather prefer you approached us and we help you out when you get stuck, because you probably will get stuck. So we can run it with Nix or without Nix. You can do it with Stack or with Cabal. All these paths are possible, but each one of them has some issues. And if you have GPU problems, then there's some more issues. So it's a rocky road, but I promise you, you will be rewarded with lots of joy. With regards to what are the contributions that could really help, there's some easy ones. So for instance, we're lacking documentation. We have many undocumented functions. Most of them are actually just copy clones of the PyTorch ones. So if you go to the PyTorch help, you will probably find an answer for what these functions do, but we don't have any help yet. Apart from that, the typed API is still not functionally on par with the untyped one. There are many functions not finalized or implemented fully, or with the right typing constraints. So if you're I don't know, a type-safe developer, who knows a bit of Haskell type families and type calculations and want to help out, you're more than welcome to approach us and help us, or just check it out and see what you can do.
Okay, we have one question from Barry, and just so we can move along, that might be the last question, unless something urgent comes up. We can also ask more questions at the end, but I don't want to make Richard wait much longer.
Hi, Torsten. Quick question. So you have the data sets. How is the data loader emulated here?
Okay, so we didn't try to do a one-to-one translation of the PyTorch data loader. if you're familiar with that one, I think it's just a class, and there are like two flavors. There's like map-like loading, and then there's stream-like loading. So we have something very similar, but basically what you do is you define this data set, and what you can think of this being is basically you define a suspended calculation for each of the items in the data set. And then these workers that are initialized when you actually, when you initialize or when you pull the first time from the stream, they will, each one of them, get a stream of working units to work on, and will then do this in parallel. This was the contribution of Andre De Prado. Not sure if this answers your question.
He says great thanks in the chat.
Okay,
so
cool.
And if Richard doesn't mind waiting, we have one more question. Thank you. Gives me the thumbs up. Cool. Leandro has one more question. Go ahead, Leandro.
Hello.
Hello.
Torsten, great talk. I have a very short question. In the beginning, you mentioned that there was a Python implementation, a similar Python implementation to your library. But the main difference between those two implementations was that your implementation supported differentiation.
Oh no! This was not what I wanted to say. So the PyTorch version of this library is the main version. So like all the big money and all the big contribution goes to PyTorch. Actually, PyTorch is quite a big thing. If you put it on Google, you get millions of results. And I think the biggest driver behind PyTorch is Facebook. They of course support differentiation. They implemented it in libtorch, and this is all they're doing, and others of course. But what we are doing is we're building this new library around libtorch, and we're piggybacking basically on all their great work with regards to differentiation.
Okay. So you also support differentiation by supporting PyTorch. Okay. Yeah. Thank you.
Yeah. Thanks for the question.
Yeah. Thank you.
Thank you, Torsten.
Thank you.
Very, very cool stuff. And now we're moving on to Richard Feldman, who I've always known as the Elm guy, but I don't think he's talking about Elm this evening. I don't think he is.
Elm will certainly come up.
Okay, cool. Well, thank you for your patience. Hard for me to know how the timing would work out, but actually I think it's been, really great to have more time for everybody. So
cool.
The show is yours.
All right. Sounds good. Thanks. Let me share my screen here. Oh, cool. I need to grant Zoom preferences, or permissions rather. Sorry, I'm on my personal laptop, and it looks like I've never actually used Zoom on this, or I never used the screen sharing on this.
Yeah, no worries. I just upgraded my Mac OS, which for some reason withdrew all of my screen sharing privileges, which I then had to go figure out how to restore. I'm stalling for you.
Yeah, I appreciate that.
I need to prepare some jokes or something. Flavio says you might have to restart Zoom.
Oh, that's annoying. All right. Yeah, and so what's weird is that under system preferences, the only thing that it allows me to do screen sharing with is like Firefox. There actually isn't anything in there for Zoom. Wow.
Yeah, if you restart Zoom and try to share your screen, it might ask you.
Right. I'll give it a shot. I'll be right back.
Yeah. Okay. Yeah, I had this problem with everything I needed to share my screen with. You have to restart and then hope it asks permission, right? So Torsten, since we're waiting for Richard, do you want to start your video again real quick?
My audio was gone. Yeah, hello.
I didn't have any questions, but I actually work on a data science team, but I'm not a data person myself. I know they do some ML things, I'm just curious if you're intending Hasktorch to ultimately be like a feature complete replacement for PyTorch. I don't know anything about this domain. I'm just curious what the goals are.
Yeah, I mean, of course, the goal is always to take over the world with these. Yeah. No. So to be honest, we don't know either. Of course, it would be a bit of a stretch to assume that like this could be a big thing in machine learning at some point. Basically, what we're trying to do at the moment is just to see if it's even possible to bring like some of the typing nicety that Haskell provides to machine learning and see how this would look like. Because I think this has not been done. Like functional differentiable programming, if you look it up, you won't find much. And surely nobody has really written real programs or even addressed research problems with this. So I think at the moment it's a big playground, and we don't really see yet what the big draw will be, or like what the beachhead for this could be, right? So one thing is, for instance, I mentioned in the beginning that Chiara, that she had finished a thesis using Hasktorch, which was in the domain of program synthesis. And this is interesting to me myself as well. The prospect of bringing together basically what Haskell is very good at, namely interpreters, compilers, and like machine learning, is to me there's a big opportunity here to basically make it possible to work on like programming language theory, design, and also like basically super smart autocomplete for code, right? So you've seen that maybe Microsoft is working on bringing some of like these big language model techniques to VS Code. So like I think there's a beta program for you to check out where you can download a plugin that then auto fills and auto completes large stretches of code. So not just the next thing, but like many lines, maybe even of code. But at the moment, this is really just learn from raw data. So basically by looking at GitHub and see what people have been written before. But it's comes without any like typing information or any like insight into the semantics of the code that go beyond like the statistics that you can derive from the data as it appears on GitHub. So what I'm interested in is, for instance, how can we bring more typing information from the compiler into this and make it more resilient so that the code that is generated there is actually also logically sound. It doesn't have any typing errors. So that would be one way or one thing to look at. But there are many others. Depending on who you ask in our team, they will give you a different story of where we would be heading with this. But thanks for the question.
Yeah, I mean, it's pretty cool that you already have people using it in their research.
Mm.
Richard is still having some Zoom issues. He is trying to rejoin again from his browser, so we'll have to wait to see if that works. Maybe I can bug Flavio now to help me fill the airtime. Flavio, what about your vision for mu-haskell, and when do you expect it will be production ready?
Well, regarding to us, I forgot to mention that right now we support things like, for example, tracing and statistics and stuff that you would normally expect for microservice like frameworks to allow. So as if you ask us, we would say it's production ready, but obviously until nobody does it, we won't know 100% if it's production ready. But there are many things that we try to, logging is supported, tracing is supported, and we supported some frameworks as well to do those things, and people should be able to add those wrappers around our servers. So sounds nice.
Richard is taking over.
Perfect.
So Richard, are you there? I can't hear you if you're talking.
Wait, how about now?
Yes, I can. Yeah, I can hear you.
Okay, cool. And you can see my screen?
Yes.
All right.
Are you on an iPad, Richard?
No, I'm now presenting off of a the in-browser version of this. So for whatever reason, my Zoom permissions like don't. I don't know. I gave Zoom as many permissions as I could, but it doesn't seem to be enough to screen share. Not going to troubleshoot that right now, so I'm now joining from a browser. And hopefully we're not experiencing a lot of lag. Can everybody hear me okay?
This seems fine. You know, with patience and humor, we can solve any technical problem.
All right, great. Well, thanks everybody for your patience on that. Okay, cool. So this is a preview of the Rock programming language. I'm Richard Feldman. So we're going to talk about 4 things today. We're going to go through them pretty quickly, and then we'll do questions at the end. So we're going to start with an overview of the language, then a quick demo, and talk about some of the goals of the language and so the progress, like where we've gotten so far. Okay, so let's start with talking about Elm, which is the inspiration behind this language. So Elm has been, for about 6 years now, my favorite programming language. Elm is billed as a delightful language for reliable web apps. That's what it says on elm-lang.org. Full disclosure, as someone in the meetup earlier mentioned, I have this book, Elm in Action, that I wrote for Manning. I'm a huge fan of Elm. And some things about Elm that I particularly like, it's a pure functional language, so no side effects, all values are immutable. 100% type inference, like you never have to annotate any of your types. It's got a really friendly, really helpful compiler. I would say it's like the gold standard of like the nicest, friendliest, like most helpful compiler I've ever used. Coincidentally, for what type of work I've been doing, it's focused on browser-based UIs. So it compiles to JavaScript. And that's also what my work has been focused on for a lot of my recent career. The thing is, of course, that there are many domains that are not browser-based UIs. So some of the ones that I've also worked in are servers, command line applications, desktop UIs. I've done all of these, and whenever I've done them, I've always kind of wished, I wish that I could get that same Elm-like experience that I really love about making browser-based UIs, but in these other domains. There are also other sort of domains that I haven't worked in, but that I'm interested in, like database extensions, editor plugins, robotics. And whenever I get into one of these, it's always like, oh, I want to write this Postgres extension, but I'd have to do it in Python or I'd have to do it in JavaScript. And I'm like, I wish I could do it in at least an Elm-like language, even if not Elm itself. So basically, I want this Elm-like experience in other domains, and not just one domain. Like a lot of people say I'd like Elm on the server, but I mean, in particular, sort of the long tail of domains, just like all of them. Separately, I'm also sort of interested in language design. This is something that's been an interest for me for many years, like even before I got involved in Elm. And I've had various ideas that I would sort of be interested in exploring in an Elm-like language, but which don't necessarily make sense for literally Elm itself. So the opportunity to explore language ideas from a blank slate for a new language, putting these two things together made me say, you know what, I think I want to pursue this. I want to actually make a language for sort of the long tail of domains and getting like an Elm-like experience. Which brings us to Rock. Rock is the result of these efforts, or at least the work in progress of these efforts. So Rock's tagline is, it's a language to help anyone create delightful software. And I'll talk a little bit more about what I mean by that later. So Rock is a direct descendant of Elm. It's similar, but not the same. So one of the biggest differences is that Elm compiles to JavaScript, whereas Rock compiles to binaries. That is like direct to machine code. Elm emphasizes small compiled assets, which is very important if you're building browser-based UIs. Whereas Rock does not. Rock kind of goes in the other direction with a monomorphizing compiler. So what this means is essentially we sort of maximize runtime speed, but the way that we do it is using this compilation technique that's also used by languages like Rust and C++ and in the functional family Milton to sort of get more runtime speed at the expense of having larger compiled assets. But again, as far as I'm concerned, Elm sort of has browser-based UIs covered, and in those other domains, I think runtime speed is a lot more important than asset size. Of course, the two languages have a lot in common. So in both languages, all functions are pure, all values are immutable, 100% type inference, and no null or nil or undefined or anything similar to that. Okay, let's move on to a quick demo so you can kind of see some of the stuff that we have right now. I'm just going to do Rock REPL. Everybody see this okay? Font size big enough, hopefully?
This looks pretty good to me.
Okay, sounds good. Yeah, so we'll just start with some basic addition, like 1.2 plus 3.4. So if you've seen the Elm REPL, this looks pretty similar. We print out the value as well as the type. So that's like adding two floats together. We can also do some like string concatenation. So you can go, hello, Berlin. There we go. I can also do a little bit fancier version of that where I can say greeting equals hello and place equals Berlin. And this is a extremely recent feature, as in just merged it last night, which is string interpolation. So we can do greeting and then put a comma in there, place, and a couple more exclamation points. There we go, bam. So these are just like some sort of basic bread and butter stuff that you would expect from a functional programming language. Like Elm, we have a really high value of wanting to have really nice error messages. So just demo one of those. Like most ML family languages, we don't allow heterogeneous lists. So if I were to say like 1.1 and 2.2, and then I were to call a function here like list.length, an empty list, now I have made a function where I have two floats in it, but then list.length, of course, returns an integer. So this is not going to compile. And the error message we get is type mismatch. This list contains elements with different types. It's got a little red squiggly under the one that is the problem. This len call produces int. However, the preceding elements of the list all have the type float. I need every element in the list to have the same type. And then a little tip, like here's how you can convert between ints and floats. So if you've ever used Elm, this error will be extremely familiar to you. In fact, if if you lined up the error you get from Elm and the error you get from Rock side by side, they're almost identical. We're really trying to follow very strongly in Elm's footsteps here because, again, I think Elm just does an amazingly great job of this, and we want to try and live up to that standard. So this is a demo of like some of the things we can do with Rock right now. We can also define functions. Chad, who's also in the meetup, recently gave us our first higher order function, which is list.map. So I can do, let's do integers this time. So 1, do like hexadecimal notation, I don't know, 3, and we'll just double those. So this is like anonymous function syntax, same thing you'd find in Haskell. So the same basic thing. You can see kind of like parameterized types here with list and so forth. Okay, so this is like kind of a little bit of a taste of like how far we've come. You can't do a whole lot more than this in the language, and in fact, there are various ways to break the REPL by putting in things. You'll get like it'll crash with a to-do not implemented yet. So I don't want to give you the impression that this is like a fully formed language yet, which it absolutely is not, but rather that like we have made substantial progress already, and you can already do quite a few different things with the language. Okay, let's talk about performance a little bit. So for this portion of the talk, I'm going to talk about a benchmark, which might seem a little bit strange, but then you'll kind of see why a little bit later. The benchmark is handwritten quicksort. So quicksort, if you're not familiar with it, is an algorithm that is extremely imperative. This is an algorithm which, if you tried to write it in a pure functional language, in a pure functional style, like only using pure functions without, sort of contorting yourself to use like a state monad or something like that, to just like really write quicksort using only pure functions in a pure functional style, by default, it's just not going to be fast at all. And so the reason we chose this as a benchmark is that this is sort of a pathologically difficult benchmark to do well on for a language where all values are immutable and all functions are pure. So obviously, like pure functional programming, I don't think I need to tell anyone in this meetup, has a lot of really nice characteristics to it. But one of the areas which is arguably a pretty significant downside is that when you're trying to implement an algorithm like quicksort, which requires mutation to be fast, you don't really get that. You don't have a first-class concept of mutation, and that makes it hard to do something like this quickly. So we can kind of see this in this little visualization of why that's the case. Here's the array. We're quick sorting it in place. And periodically we do the swap operation like this. And every time that swap happens, either it's going to happen in place like this, in this mutation-y example, or here's another swap. In a sort of pure functional version, you would theoretically need to clone the entire array and then copy in like new values into the new clone, which would be quite a bit slower than doing the mutation in place. And yet, this is what we've decided to benchmark Rock against. So here's quicksort, or at least a portion of quicksort in JavaScript. So we can kind of see some of these mutation-y things in play. So here's a for loop, an imperative for loop. We're calling the swap function, which mutates the array in place. We're incrementing an index. We're calling swap again to mutate in place. Really, there's just like most of this function is what it's doing is in place mutation and imperative programming. In contrast, here's the pure functional equivalent in Rock of the partition function. You can see a little bit more Rock syntax here, but not going to really get too far into the weeds on syntax. Notice that, by the way, we're returning a record here. In the JavaScript version, we didn't even need to get records involved because we were just able to mutate things in place. We're returning another record from the other branch here. We're actually calling this other helper function called partition help, which is even longer than partition. We didn't need a helper function in the JavaScript version. This partition help function is also returning records, and it's recursing on itself. So if you put these things side by side, you can really see that this is not a problem where pure functional programming shines. Shines in plenty of other places, but really not something like this. In fact, I'm willing to call this sort of a pathological algorithm for pure functional programming. Okay, but this is about a benchmark. So we looked at how does this imperative JavaScript version compare to the Rock version, and we also threw in a couple of other languages like Java, Go, and C++ to just benchmark like how long do these languages take using, on the one hand, an imperative algorithm that's basically exactly the same as the JavaScript one for the other 4 languages, and this pure functional one in Rock. And we ran them on quick sorting 1 million numbers, so we could get sort of a big enough data set to get some sort of signal there. And here were the results. So this is time spent to quicksort 1 million unsorted numbers. So unsurprisingly, C++ was the fastest at this with the imperative mutate in place algorithm. Go was slightly slower than that. Rock was only slightly slower than Go and way faster than JavaScript or Java. Now keep in mind that this is an unfair benchmark because it's extremely unfair to Rock. All of the other 4 languages got to write a mutate in place, like just imperative go through and do a normal textbook quicksort, whereas Rock was the one that had to do this pure functional version that's like twice as long and involves records and recursion and all that stuff. So we're pretty excited about this result. We just got this in August. We'd been sort of building up to being able to see how this benchmark would do, and the results were obviously very exciting because a pure functional language, quite frankly, has no business being this fast. But this is what we were designing it to do. This was a result that we were hoping for. In fact, we were kind of hoping that we would catch Go, and we kind of think that we should be able to with some more optimization work. But there was a lot of like careful optimization work that went into just getting this early result. Okay, so how does it run so fast? So I'm going to talk about 3 aspects. 2 of them I'm just kind of going to gloss over. So monomorphization, I mentioned this earlier. This is a compiler technique that like C++ and Rust and Milton use. Rock is using it as well. We're also using LLVM as a backend. LLVM is really good at producing efficient machine code. Not a whole lot to say there. It's just a technique that we've chosen to use. Automatic reference counting with static elision. This is a little bit less common in the functional world. Actually, I don't know of any functional languages other than the research language we're going to talk about a little bit later that use this. Most languages use a tracing garbage collector, but if you look at like Rust and C++, and Swift also uses this, and NIM is another language that recently introduced automatic reference counting. It can be a way to avoid GC pauses. And finally, the one that I do want to talk significantly about is opportunistic mutation via uniqueness analysis. So let's sort of zoom in on that a little bit. Opportunistic mutation. So like I said, semantically, Rock is a pure functional language where there is no notion of mutation, no notion of side effects. All values are semantically immutable and all functions have no side effects. But that doesn't mean that the compiler has to compile to code that doesn't do any mutation. That just means it needs to not be observable to the programmer. So here's an example of some Rock code. Let's say I define this point. I've got a record. It's got x of 0 and y of 0. And then I decide I want to define a new point that's based in some part on that point. This is using Rock's record update syntax. If you were using Elm, this would be the same thing, except the ampersand would be a pipe and the colon would be an equals. Basic idea here is what this syntax is saying is start with this point record, and I want to make a copy of it where all the fields are exactly the same as before, except I want to change the x field to be 5. And we could do this again and say 0.3 equals 0.2 with an update of copy everything that was in 0.2 except make the y field be 10. Well, if you look at this code, if we were to imagine what this would compile to in most languages, this would be sort of multiple instances of copying records here. Like every time you do this record update, it's going to have to copy an entirely new record from the previous one because that's kind of the whole point of immutability. But we can make this observation that, okay, if I look at where point is used, after this point in the code, this point value is never used ever again. It never comes up again. So we don't really need to copy it. We could just kind of quietly behind the scenes mutate it in place, and it would not change what the program does at runtime at all, except for making it faster. It wouldn't change the observable outputs of the program. It would just be a performance optimization. Similarly with 0.2 here, actually. 0.2 is never used beyond this point, so if we wanted to, we could just have the compiler say, you know what, I'm just going to go ahead and reuse the previous memory that we had here. So actually, if you look at all 3 of these put together, we could be taking that same chunk of memory that we originally started off with in point and just actually be semantically using it immutably, but at runtime, it's just going to be mutating in place over and over. And so you can imagine how using optimizations like this could help us out in the case of quicksort, where semantically, we've written code that is immutable and all pure functions, but actually behind the scenes, it's compiling to something much closer to what C++ and what Go were doing. There is a programming language that does this. It's a research language called Clean, which comes out of, I apologize, I'm going to butcher the name. I'm an American, Radboud University. I know that's not the correct Dutch pronunciation. So Volkert, who is one of the people who's been most active in Rock's development, who's also in the meetup right now, recently actually is now officially a Master of Science from this university. And so he's been working with some of the people there to do a master's thesis. His master's thesis was on basically taking some of the ideas from Clean about this uniqueness analysis and doing them in a really high performance way, which is to say, like, making it so that the compiler can do this analysis really quickly. And he's implemented that in Rock. And that's basically how we're able to be competitive on Quicksort, and why we chose Quicksort as a benchmark, because if this worked out the way that we wanted it to, we were like, yeah, actually we should be quite competitive at Quicksort, even though it's written in a pure functional style. A reasonable question might be, how long do these optimizations take? Is this something you're going to be sitting and waiting for a week for your code to compile? Short answer is no. So if I run rock build --optimize on quicksort.rock, it takes 0.28 seconds to compile on this 4-core MacBook Air that I'm presenting from. Almost all of that time is spent in actually like LLVM and linking. The actual like Rock compiler that's like doing the optimizations takes something like 60 milliseconds to build, like start to finish, including like loading the file, parsing, type checking, and doing all the optimizations. So most of the work there is being done in LLVM and afterwards. So yeah, it's pretty fast. And granted, this is, at this point, quicksort.rock is the longest Rock program in existence. So I can't tell you like how long this would take on like how long Rock would take to build a million line of code base with or without optimizations, because that code base doesn't exist yet. But I can say that we've designed for that, and it's really important to us that the compiler be fast, in addition to producing fast code. The way that we've achieved this speed so far is by writing it in Rust, and the plan is to keep it written in Rust, never to self-host, just have it be a Rust compiler, because I think, quite frankly, Rust is excellent for programming language for making really fast compilers, and that's what we want to build here. Okay, so we're going to talk about some of the goals for the language, and then finally talk about the progress we've made so far. So I mentioned earlier, Rock is a language to help anyone create delightful software. Let me be a little bit more specific about what I mean about delightful software. So first thing is, I would say delightful software runs fast. So we are prioritizing runtime execution over compiled asset size. This is like one of the fundamental trade-offs that Rock makes compared to Elm. Elm, also a very fast programming language within the domain of browser-based UIs, but of course compiled asset size is a very important consideration that we have the luxury in Rock of not considering, because we're saying, Elm has covered that domain. I'd say delightful software is reliable. So we try to help the programmer identify problems at compile time rather than at runtime. So things like, if you want to get something out of a list, that's not going to return, null or undefined or crash. This is going to give you, a sum type wrapper around the results. And finally, delightful software is user-friendly. Now, from a language perspective, there's not a whole lot that a programming language can do to help you make user-friendly software, because a lot of that work is design and iteration. But what it can help with is by providing really nice tooling for helping people do iterations on their design towards a more user-friendly piece of software. So we want to accomplish that by providing quick feedback loops via a really fast compiler and a really fast and really helpful editor. So let's talk about that. This is all, from here on, I'm going to talk about stuff that is purely aspirational. We haven't really started this work at all in terms of implementation. So I don't have a REPL-style demo of this, but it's a really important part of the project. So there's a lot of really inspirational talks out there about like amazing potential editing experiences that we could get on computers. So one of the most well-known names in this space is Brett Victor. He gives demos about some of the stuff that like inspired some of Elm's tooling, like the time travel debugger. He has some great talks here. Inventing on Principle is probably his most famous, but he also has some really nice ones. Media for Thinking the Unthinkable, and some written stuff he's had on his website, Up and Down the Ladder of Abstraction. There's also some really cool stuff as far as functional programming and having better introspection into your types in your editing experience. So one example of functional programming stuff in terms of like editor possibilities, this is a Strange Loop talk from Professor Robbie Chugg, where he shows this sort of bidirectional editing experience where you have you're editing something on the right, and then on the left it's sort of syncing with the code that you have written, whether you're doing like the WYSIWYG editor or you're writing in the code. The two are sort of aware of each other, and you can work in either one depending on what you're trying to iterate on. Also, Cyrus Omar gave a great talk about, also at Strange Loop a couple years later, about doing a programming with typed holes in like a really tightly integrated way with your editor. And both of these talks are things that I think absolutely should be the norm. I think these are things that should not be just academic experiments in research languages, but are things that we absolutely should bring to the mainstream. And those are some of my goals and aspirations with Rock when it comes to editing experience. But the most influential thing that's on the stuff that I want to talk about next is this talk from Aditya Siram, aka Deech on Twitter, and in GitHub. And he talks about what functional programming can learn from Smalltalk. And he gives this sort of extensive demo of Smalltalk tooling and like in particular Pharaoh Smalltalk on like what the IDE experience is like in that world. And at the end, he concludes with a really, really strong point, which is whatever functional programming community you associate with, this community that's built this tooling is smaller than that. And the reason that they've been able to build this tooling is that they have a really strong culture around having a shared value of everybody uses the same editor, everybody contributes to the same editor, and everybody has really high standards for that editor. And he concludes with the point of, you know, if you want this in your community, the first thing you got to do is inspire people to want that, to have those high standards, to have those high expectations for their editor tooling. And since we're starting from a blank slate with Rock, I see this as a great opportunity to do exactly that, to have a community-driven approach to like, hey, let's all use the same editor and contribute to the same editor together to make an experience that's really not possible otherwise. So some of the editor goals. Number one, ships with the language. Like you download the Rock binary, you get the compiler, and you get the editor. Those both come standard. There was nothing separate to install about it. Number two, the scope of the editor is Rock code only. It's not a general purpose IDE. It's not for editing JavaScript. It's not for editing HTML. It's not even for editing JSON. It's just for editing Rock code. And that narrow scope, I think, is the only hope that we have of achieving these other lofty user experience goals, is by saying this editor is laser focused on being for exactly one programming language. Number three, all interaction feels instant. Brett Victor talks about this a good bit, but also this is just honestly, personally, something about standards. Like I think that we can achieve an editing experience where you basically never see a loading spinner unless you're working on thousands or maybe millions of files. Like if you're doing a find replace across your entire project, you have an absolutely enormous project, okay, fine. At some point, we're limited by the hardware. But if you're typing and you're waiting for an autocomplete to finish, I think we failed. Like everything should appear instantly, and that's really the bar that I want to set for like the interaction in the editor. And again, seems very achievable using modern hardware and the right software techniques. We'll see if I'm right, but that's what we're aiming for. And the fourth and sort of biggest, maybe most ambitious part of this is to emphasize package-specific integrations. So let me give you an example of what I mean by that. Let's suppose that we wanted to have an editor plugin for a regex assistant. So here we have a regular expression for validating US phone numbers. And regular expressions have this reputation of being, quote, write once, read never. They're sort of inscrutable. Like you look at it and you kind of stare at it and you're like, okay, I kind of see what this is doing. But if you had to debug this and say like, what if I told you there was a bug somewhere in there? Could you spot it? How long would it take you to spot it? How long would you take it to figure out? They're not really very user-friendly in terms of a reading perspective. So what if we had, like imagine I have my code on the left, which I blurred out because it doesn't matter. And then on the right, we had this sort of regex assistant that's like an editor plugin. And all this is it displays the regex that I'm working with here, and then I type in my input here that I want to validate against the regex, and then it just shows me the capture groups and where they've matched. We get a little scrubber here where I can kind of go step through and say, okay, so first I'm matching 1 and then 2 and then 3. Oh, I see. This is highlighted because this is what's matching. I can watch the capture group sort of advance as I go through this. I can scrub all the way through and just see how it's actually parsing some particular piece of text. Now, I don't know about you, but for me, being able to interact with this way and sort of scrub back and forth and watch what it does is way more helpful than just seeing this text or even just seeing this text with syntax highlighting. Now imagine if I could have this regex assistant plugin, but this was not something that was baked into the language, and it was not something that was baked into the editor. This is just a plugin that someone shipped with a regex package. Like they said, I'm going to build a package for parsing regular expressions and working with them, and I'm going to ship that package, put it on a package registry, and whenever anyone installs that package, they get, of course, they get the code. They also get the documentation, as is standard with installing a package. And also, they just get immediately, instantly, without having to do any extra work, this plugin added to their editor. And that's just something they can just pull up now. Because they installed the package in their project, their regexes just get this tooling now. And then imagine that it's not just for regexes, but imagine if that were a cultural norm across all packages. Like anytime someone builds a Rock package and ships it, it's this cultural norm that you ship the code, and of course you write documentations, and of course you write a custom editor integration that helps people interact with it. For my money, that's something that we've never seen, and that's something that is so potentially valuable that it's worth pursuing really aggressively. And I don't see why we should aim any lower than that. It's something that, as far as I am aware, it seems to exist only in the Smalltalk community, is having these sort of like user-defined plugins on a per package or per module basis. And I think it's something that FP can benefit from just as much. So that's where we're sort of aiming with the editor. Okay, and finally, I want to just wrap up with like progress, and like here's where we are right now within within this sort of like grand vision of where we want to get to. So we started in 2018. So this was like, I had some initial ideas about the design, wrote them down, figured out some points, sort of hashed out how the language is going to work at a high level. 2019, I made the first commit. And then also in 2019, we had a couple of different people join the project. And by far, the three biggest contributors have been me and Folkert, who's also on the call, and Chad, who's also on the call. Folkert has done a lot of stuff with optimizations. So when we saw the quicksort benchmark, that was largely Folkert's work. And Chad has done more work than anyone else on the standard library, which is really tightly intertwined with the integrations, with the optimizations, because without the standard library having like special annotations so that the compiler knows when it can do the in-place mutations, none of that would work. So when you saw like list.map and stir.concat earlier, Chad implemented both of those, among many other functions in the standard library. So thanks to both of them, because it's really hard to imagine this project without either of them at this point. So here we are in 2020. We now have our first application, which was Hello World, followed shortly after by Quicksort. Now I can imagine a possible future here. I don't want to call this a roadmap. I don't want to make any commitments here or even any estimates here. This is just like a possible future that I could see plausibly playing out in my head. Certainly I would think by 2024, I would be surprised if by then we didn't have at least some sort of 0.1 beta release, like a public release. But I see that there are a couple of prerequisites before then, and to be honest, I don't really have any idea of how long those might take. So I think it's probably somewhere in the 2022 to 2024 range. So I think 2021, it seems safe to say that there's a reasonable chance that we'll be able to build useful applications. I mean, right now we can do quicksort, but there's actually no realistic way to do like I/O in the language yet. It's on the roadmap, obviously. That's a really important part of making a useful programming language, but we just haven't gotten to it yet. It's just not implemented yet. So if you're wondering, can I go home and use Rock to build my X? The answer is probably no, unless it's some like pure functional algorithm, then maybe. But realistically, no. It's really just not useful for anything yet. We're just still working on it. 2022, I would like to think that hopefully by then we could have an editor that's not just like extant, because right now it doesn't exist, but also useful. So not to say that it's like, amazing, it's fully featured, it's like, wow, this is straight out of a Brett Victor demo yet, but rather that it's like, it does something useful, you could potentially use it for daily editing, there are a bunch of features missing, it doesn't have any plugins yet, etc. And then maybe 2023, the editor is actually extensible, we have like plugins that you can write. Of course, the plugins will be written in Rock, and now you can, extend it in useful ways. But I do see that last step, the extensible editor, as, in my mind, that is sort of the prerequisite for doing a public beta release with like a real version number and stuff. I think up to that point, in my mind, the intention is to keep building from source right up to that point where we have the extensible editor, because as Deech, I think correctly identified in his talk, if you want to get that editor experience, it's really important to have that be a cultural value, like from the very beginning. And so before we sort of start opening this language up and saying like, hey, let's start forming a real big community around people building stuff with this language, I want to try and have that ready to be a community value on day one, like it was for Smalltalk. So again, I don't know how long these things are going to take. Maybe we're done with it all in a month. Highly unlikely, basically impossible. Maybe it takes even longer than this. I also think that's unlikely, but somewhere in this range, I think this is sort of like what the possible future of the language might look like. Okay, so Rock is developed under an Apache 2 license. For right now, the repo is private, basically because in the state that it's in right now, I don't want it to get on Hacker News or Twitter or like, shared widely yet. But that said, like, it's not a secret. It's just, I just don't want, that like social media level of explosion, because it is still in its very early days. So if you're interested in this project, like you want to see the code or just like take a look at it or play around with it, just feel free to email me and I'll just like invite you to the repo. It's really like not a security thing. It's just wanting to control how it gets shared for right now while it's still in the early stages. Last but not least, I wanted to mention like who's making the language. So me, Folkert, and Chad, and possibly you. So one of the reasons that I wanted to give this talk at this meetup is we would love to have more people get involved in this. none of us, I should mention, like knew really that much about like any of the technologies that we were working with when we got started. I would say there's like absolutely no experience necessary, just interest. Like none of us really had done anything serious with Rust, and now we've written thousands of code of a Rust compiler, and none of us had really had much experience with compilers. We all just kind of learned on the fly, and I'd be personally happy to mentor people, get people up to speed on the code base, you know, if you're interested in getting involved and contributing to it. And again, if you're interested in doing that, send me an email. So thanks very much, and happy to answer any questions people have.
Thank you very much, Richard. That was super inspirational. I've never seen, well, I didn't know about the Smalltalk editor integration, but I haven't seen this custom editor integration idea on any roadmap for any language before. So I'm particularly excited by that. We do have some questions, I think.
Cool.
Well, Flavio seems to have like 5 questions and 3 comments. I think he's very excited. So maybe he wants to unmute
Cool.
and unload.
Sorry, maybe I can just ask one, another person can ask another one. Well, basically, one of the stupidest questions is like, for example, if you're going to allow something like infix operators, because seeing that map with the arguments flipped was kind of like wrong for me, but just wondering if it has infix operators.
Good question. So the plan is, like Elm, not to allow custom operators. The reason the arguments are flipped has to do with how the pipe operator works in Rock, and it's actually to, well, yeah, I don't want to get into a whole like thing. That was intentional, an intentional design decision. And wow, this is interesting. Am I flipped? It looks like I'm like because I'm using it in the browser. At least the thing I'm seeing of myself, it looks like it's mirrored. That's interesting. Anyway, yeah, short answer there is no. That's the plan is not to do that.
Yeah, I think, well, I've been involved with the Reason ML world as well, and they had a similar problem with a pipe operator, to the point that they had to invent like the OCaml pipe and then a fast pipe that pipe to the second argument because of performance reasons and type inference. So maybe you're running into something like that as well.
Oh no, it's not a problem. It was just an intentional design decision. Like we very easily could have done it exactly the same way Elm did. Just decided to go in a different direction. There are trade-offs to both approaches, and this is less familiar to people used to like Elm and Haskell. But there is a benefit. Again, like I don't want to get super in the weeds on one small design decision, but yeah, it's an intentional choice. It's not like there was a limitation. We could have just as easily gone the other way.
Okay. Also, another question. I just copy and paste like the canonical Haskell implementation for quicksort, like it's 2 lines of code. And I was wondering if Rock with such an implementation would be as fast as the benchmark you showed, or it would be a little slower.
Good question. To be honest, have no idea. I'm familiar with the code that you're talking about. It's sort of like an elegant quicksort. It's like very, very concise. So I would argue that is not quicksort. I mean, it's a sorting algorithm, but like when I look at it, I'm like, nothing about this is like mechanically doing the same things that quicksort is doing. So I don't think it's reasonable to call that quicksort. But that's just me personally. Others may disagree. But yeah, so what we tried to do is we tried to basically say like, okay, let's try to take the same like operations that quicksort is doing in terms of like how it's like swapping things and doing partitions. Because that seems to me to be like the essence of quicksort. And wherever we can't do something in place, let's do the pure functional equivalent of that. But you know, try to keep the same, like do the partitioning, do the swapping, like try to keep it in as close in spirit as possible to like actual quicksort, like the traditional one.
My last question, sorry, is how did it feel? I want to know a bit of your feedback. Working, for example, you worked in the Elm compiler in Haskell, and now you're working in a new language in Rust. So what are your impressions between these 2 languages? And also, what are your feedback on working on programming languages itself, which is a domain on its own?
Sure. So I have not actually, like my contributions to the Elm compiler itself have mainly been like fixing typos. Like I can't claim to have like written Haskell code for the purposes of like making the compiler better. Honestly, that's just because like I never really like knew it well enough. Basically everything I know about compilers I learned by making the Rock compiler. And I think that's probably also true of Folkert and Chad at this point. They can correct me if I'm wrong. But that's my impression. Yeah, so I can't really compare, like it would be kind of an apples and orange comparison, but I can say that, I mean, like we very directly looked at the code in like the Elm compiler, and like a lot of the time, like, you know, like the type inference, for example, is directly like a translation of what Elm is doing from Haskell to Rust. And in some cases we were like, there's a bug here. Why is there a bug here? Let's go look at exactly what Elm was doing and like step through like line by line and like print out what the state is at each thing. It's like, oh, well, we were differing from Elm here. Let's change it, and the bug was fixed. So I mean, like really, it's like the same algorithm as what Elm is doing. So as far as like doing compiler development itself, I would have to say that this has been the most rewarding programming project I've ever worked on. It just feels amazing. Just like, and I mean, it is quite slow going. Like it takes a long time to like, you know, you'd be surprised how long, like how many steps were involved in getting to list.map, for example, or getting to quicksort, right? But man, like just seeing it and being like, wow, this really works. This is a real thing. Is just an unbelievable feeling that I've never experienced like with any other of the programming that I've done before. So yeah, it's amazing, and I really highly recommend it.
Perfect. Thanks for answering.
Sure.
Thanks, Flavio. Leandro has a question for you.
Hello. Interesting talk. I have a very short one, actually. When you showed the comparison, the performance comparison with other languages, strangely enough, you didn't mention Rust.
Oh, I didn't bother with Rust because I assumed that Rust and C++ were going to be like basically identical.
Okay.
I mean, we could put Rust on there, but
especially since you mentioned Rust as the language in which you are writing a compiler. I was a little bit.
Yeah, so the main things that I thought were interesting there were Java and JavaScript, just because they're both like two languages that have garbage collection and JITs, and their JITs have been optimized for like decades. Go, because as far as I know, it doesn't have a JIT, but instead tries to compile the machine code, but it's also garbage collected. And I wanted to have like one thing that was sort of like, okay, what's the peak? Like you can't really get any faster than this. And I figured that's C++, which has direct memory management. And so it seemed like what I expected was C++ first, and then either Rock or Go in second place. And then I wasn't sure which of Java or JavaScript would be faster. But yeah, that was like the idea was to get a representation of like those different sort of groups as like JITted, manual memory management, and automatic memory management, but not JITted, which is like Rock and Go. And yeah, so that was the thinking there. But I would be really shocked if Rust was not like right next to C++. Like, I think the only difference between them is Rust has bounds checking, which may or may not get optimized away in that example, in which case like maybe it would be like slightly behind C++, but like the pixels would be the same on the graph, you know, like that's what I would expect for Rust.
Oh, thanks.
Thank you. So I don't see any more questions in the chat. And actually, we've gone for about 2 hours. So I think I picked the right number of talks for this evening. Richard, I want to thank you for presenting this language. Are we actually like the first meetup you've presented this to?
It's the first one I've done in a recorded session. I did a little like, I guess this is the most detailed one I've done. I did like a little, for a Philly Rust meetup, I did like a little, hey, here's the thing I'm working on. But yeah, I saw someone in the chat mentioned like the email address. I would also love to get anyone's feedback on it. Like if you have any, you know, I don't know, like, does it seem like an interesting project, et cetera? Yeah, that would be great.
Okay, well, this is going to be put on YouTube, so you'll have worldwide exposure. Whatever,
Cool.
whatever the awesome power and reach of the Berlin Functional Programming Group is worth, it's yours. So I just want to formally thank all the speakers, Richard, Flavio, and Torsten. And I'm actually going to end the recording now, and then we can do a few minutes of announcements if anyone has announcements, and general chat if people would like to stick around for a little while. So thanks again, everyone, and I'll see you at the next FP Forum.
Cool.